Hello. In this video, I would like to share information on density curves and normal probability distributions. A density curve describes the probability distribution for a continuous random variable, not a discrete random variable. Continuous random variables can take on an infinite number of values rather than a countable list. The area underneath an entire density curve is equal to 1, which represents the probability of 100%. The area under a density curve between 2 points gives us the probability an event will occur between those two values. For example, a density curve, even though it is a straight line, is provided that shows the probability choosing a value between 1 and 6 at random. The probability associated with each value is 0.2. So, in order to find the probability of choosing a value x between 2 and 5 is equal to the area under the curve between 2 and 5. Since this is a rectangle with a width of 3 and a height of 0.2, the area computes to 0.6, or 60%. Density curves are not always straight lines. Instead, continuously random variables very often follow a normal distribution, where the density function's shape approximates what is called a normal density curve, or sometimes a bell curve. Normal density curves are more dense around the center, or mean, and less dense at the tails, or extremes, which means results for trials tend to occur close to the mean value rather than much higher or lower than the mean. The empirical rule of normal distributions describes the likelihood of observing results surrounding the mean. It states that 68.24% of all possible observations occur within one standard deviation above and below the mean. It also states that 95.44% of all possible observations occur within two standard deviations above and below the mean. And it states that 99.74%, or almost all possible observations, occur within three standard deviations above and below the mean. The rule can be used to compute beyond three standard deviations, but it usually isn't needed. Example 2. Suppose that the replacement times for washing machines are normally distributed with a mean of 8.7 years and a standard deviation of 1.6 years. What is the probability that a washing machine must be replaced between the age of 7.1 and 10.3 years? Coincidentally, 8.7 plus 1.6 is 10.3, and 8.7 minus 1.6 is 7.1. So these two endpoints represent time one standard deviation above and below the mean. According to the empirical rule, the probability that a washing machine needs to be replaced sometime between 7.1 and 10.3 years is 68.24%. What is the probability that a washing machine must be replaced between the age of 5.5 and 11.9 years? These endpoints represent two standard deviations above and below the mean. So there is a 95.44% chance the washer needs to be replaced between 5.5 and 11.9 years old. What about the probability of needing to replace it before it is 5.5 years old? Well, keep in mind that the total area under the normal curve is 100%. So the area under the curve outside of the two boundaries is 100 minus 95.44, or 4.56%. But this represents the area below 5.5 and above 11.9. The bell curve is symmetric, so only half of this percentage applies to the area under 5.5, or 2.28%. Investigating probabilities will not always work so nicely with precise standard deviations from the mean. So we often use a standard normal distribution, which has a mean at 0 and a standard deviation of 1, instead of the population's true mean and standard deviation. It is easy to standardize a variable by using this formula. Example 3. A study of the amount of time it takes a mechanic to rebuild a transmission for a 2009 Toyota Camry shows that the mean is 7.5 hours and the standard deviation is 2.1 hours. If 40 mechanics are randomly selected, find the probability that their mean rebuild time is between 6.5 and 9 hours. Since these times do not fall on a multiple of a standard deviation, we must standardize the variable. To standardize the variable 6.5, we use the formula to obtain a z-score of negative 0.48. The variable 9 is standardized to a z-score of 0.71. These scores do not represent probabilities like the empirical rule. Instead, they give us a position on a standard normal curve for which we can compute the probability. This is usually done with a table of areas under a standard normal curve. The area under a standard normal curve to the left of a z-score of 0.71 is 0.7611, whereas the area under a standard normal curve to the left of a z-score of negative 0.48 is 0.3156. These areas correlate to probability percentages. In order to compute the probability between the two z-scores, we subtract the lower z-score area from the upper z-score area, since geometrically this would leave the area between the two endpoints. The probability the job will take between 6.5 and 9 hours is 44.55%. To finish this video, consider the following scenario. A school reported that the average composite score on the recent SAT test was U equals 1024, with a standard deviation of sigma equals 58. When plotted, the scores roughly follow a symmetric bell curve. Using z-scores, what are the following probabilities? We must be sure to convert each variable to a z-score and use the provided table to determine the probabilities. The variable 900 converts to a negative 2.14 z-score. Which is a 0.162 or 1.62% chance of occurring. Please pause the video now and complete the last two examples on your own. Resume playback in a moment to check your work.